Good day to you, students. I hope you guys are doing fine in your various homes. In our last class, we discussed equilibrium constant, where we spoke extensively on how to write the equilibrium expression of a reaction. Today, we are looking at a subtopic under this equilibrium constant titled Calculations Involving Equilibrium Constant. And at the end of this lesson, I expect each and every one of you to be able to calculate the equilibrium constant of a reaction. All right. To start with, there are various ways by which the questions will always be asked under this topic. We have cases where equilibrium concentrations are given. Now, in this case, let's look at an example of this. If at equilibrium, a mixture contains 0.235 molar of carbon dioxide, 0.399 molar of hydrogen gas, 0.115 molar of carbon monoxide, and 0.210 molar of water, then calculate the equilibrium constant, Kc, if the equation of the reaction is given as this. From this question, we will discover that they have given us all the equilibrium concentrations of the reactant and the product. This is the one for CO2, this is the one for H2, for CO, and for H2. So in as much as we have been given all the equilibrium concentration, all we just need to do is we write out the equilibrium concentration, constant expression, which is product over reactant. I believe you still remember this. So from here now, then you start substituting each of these. What is our CO? Our CO is 0.115. That's what we have here. Then our H2O is 0.1210. That's what we have here. Divided by H2. Where is our H2? That's 0.399. That's what we have here. Then the last one is CO2, which is 0.235. Then when you multiply everything, it will give you 0.258 as the value of equilibrium constant. But when you look at this, all the equilibrium concentrations are given. But we have cases where not all the equilibrium concentrations will be given. In that case, you make use of what is called ICE table. What do you mean by ICE table? The meaning of ICE is the I there represents initial concentration, C represents change in concentration, and E represents equilibrium concentration. That is the concentration of that thing at equilibrium. Okay, let's look at this example. When all equilibrium concentrations are not given, then we make use of ICE table. Example 1. If 1 mole of hydrogen iodide is initially, let's take note of that word initially, present during a dissociation reaction, at equilibrium, it gives 0.58 moles of hydrogen iodide, then calculate the equilibrium constant Kc if the equation of the reaction is represented thus. Mind you, at initial stage, if you are given a reactant, you should not expect any product. Product is only formed whenever the reaction has begun. Now, let's look at what we do here. All we need to do is we construct a ICE table. And this is the ICE table carrying the 2HI. This is the reactant, while these are the product. So at initial stage, this is I. Under I, initial, you have 1 mole of hydrogen iodide. That's what is formed at initial stage. But at that initial, you don't expect anything to be formed at the product. That is why we have 0 and 0 here. Now, the moment the reaction begins, the concentration of the reactant side will be reducing, while the concentration of the product will be increasing. But we are going to represent that increment by letter Y. Letter Y. And that is why we said this side will be increasing by plus Y. But the reason why we have added 1 here is because 1 is the number of mole of this I2. That is 1Y. 1 is the number of mole of this H2. That is plus 1Y as well. But in this case, 2 is the number of mole here. That is minus, don't forget we said the concentration of the reactant will be decreasing. That is minus 2Y. Now, let's now look at the change in concentration. That is C. 1 minus 2Y. That's what we have here. Then, in this case, 0 plus 1y, that will give you 0 plus y. In this case, 0 plus 1y, that will at the end of the day give you 0 plus y. Then what is now the final equilibrium concentration? This one for hydrogen iodide have been given in the question already. If at equilibrium, it gives 0.58 moles of hydrogen iodide. So that is where we got that 0.58 moles. So this one will now be, what is 0 plus y? That is our y. 0 plus y, that is y. Now let's proceed. Since we don't know, this is y and this is y, we cannot work here. This is y and this is y, we cannot work here because you have two unknowns. But in this case, this is y and this is a value that is known. So that means we can easily work here to get our y. So from that expression, that will be 1 minus y equals to 0.8. So let's now produce it. 1 minus 2y equals to 0.58. Then if you collect like terms, that will be 2y will be equals to 0.42, and you at the end of the day get 0.21. Now, if you now want to get the equilibrium concentration, or equilibrium constant of that reaction, all you need to do is you write out the equilibrium constant expression, product over reactant. Then we have already known our H2 to be y from that ice table. Our H2 is y, our I2 is y, and our 2HI is 0.58. All we just need to do is we start substituting. Our H2 from that is y, that is 0.21. That's where we got this 0.21. Our I2 is also y, that's 0.21. Then divided by, what is our HI? That's 0.58. But don't forget you are going to square it because of this number of mole here. That's 2HI. Okay? So, you square this, then if you solve this, it will at the end of the day give you 0.13. Alright, I believe with this short video of mine, I've been able to explain how we can find equilibrium concentration when all equilibrium constant when all equilibrium concentrations are given, and when all equilibrium concentrations are not given. So when we get to the Google Classroom, we are still going to solve as many as possible numbers of questions. As I expect you at the Google Classroom, I pray that God bless you all. Thank you.